Okay, can you see my screen?
Yes.
All right, so here's the first problem. Talks about an element, polonium, the alpha allotrope of it, and it says that it crystallizes into a simple cubic unit cell. The edge length of the unit cell for this element is 336 picometers. And the first question is for you to determine the radius of the polonium atom, and then to determine, based on the information provided, the density of alpha polonium. All right. Now, to help us, I included this diagram here, which shows you what the simple cube three-dimensional shape look like, or the cubic arrangement of the atoms in a cubic cell, right? So basically you have one atom occupying each corner of that cell, all right? And because, well, let me just say that this is basically what we call a space filling model. So it shows you basically how the size of the atoms are also involved in this unit cell. And you'll notice that in this arrangement, basically the atoms are touching their nearest neighbor. All right. So, for example, the atom that is occupying this corner is touching the atom occupying the next corner to it, above and to the left. All right. And the same is true for all the other atoms involved in this arrangement. All right. So, how do we go about answering the first question of the atomic question asking for? Let me go back here. Question is asking for the radius of the atom. All right. So, to do this, it's rather simple, of course, but let me pull up my writing tablet here. So you'll notice that going back to the question, let me bring this over here to me. You'll notice in the diagram for the unit cell that basically one full length of the edge of the cube would be equal to two radius length, right? So you have one radii here for this atom and another radii here for that atom. So therefore, the answer to the first question is rather easy. So the answer is that since the length, oops, oh shoot, this is not plugged in. I'm sorry about that, folks. Give me a minute here. Okay, now we're in business. So since the length would be equal to the length of one edge of the cube, will be equal to 2 times the radius of one atom, then that means, of course, that the radius will be equal to L over 2. And the length, as we said before, is equal to 336 picometers divided by 2. So according to my calculation, this is equal to 168 picometers, all right? So that would be the radius of the atom. Now, the second part is asking for the density. So this is the answer to the A part, right? For the second part, the question is asking for the density. Now, the density, of course, will be equal to the mass divided by the volume, right? Now, the volume is the easier one to determine. The volume, is equal to the length of one edge raised to the third power. So that will be equal to 168 picometers raised to the, 336 picometers raised to the third power, right? Because that's the length of one edge of the unit cell. So let me see here. According to my calculation, this would be equal to 3.79 times 10 to the 7 picometers. Let me just confirm that. I did that this morning. I did this work this morning. So let me confirm. 376 raised to the third. Oh, something is wrong here. So that's why it's a good thing to check your work or recheck your work. 37. Oh, it should be 336. 336 raised to the third. So yes, that's correct. 3.79 times 10 to the 7 picometers. All right, cool. So that's the volume. So the real challenge is the density, or the mass, I should say, to get the density. Now, the first thing we need to find out is basically the number of atoms present per unit cell. And if you look at the diagram, let me go back to the diagram right here. And this calls for you to actually get a good feel for the three-dimensional arrangements here. If you look at this diagram here, right, you'll see that each, and if you consider that what will happen beyond just this unit cell, you're going to have a unit cell next to it, to the left, to the right, above, and below. What you'll realize is that each atom in the unit cell is basically being shared between 8 other unit cells, right? So basically, the atom represented here is basically 1/8 of an atom, all right? Because the rest of it will be shared among the unit cells immediately surrounding it. And the same is true for all the other unit cells in this structure, all right? So because there are 4 corners being occupied by each atom, and it's 1/8 of each atom present in this unit cell, what that means, therefore, is that for the polonium element represented here, the number of atoms in a cell will be equal to 8 times 1/8, which is equal to 1. So there'll be 1 atom per unit cell, all right? So basically what we need to find out now is the mass of that atom in the unit cell. So the way we start with it, we start off with 1 polonium atom per cell. And then we do the mole of polonium. This should be PO, not P, right? We find the ratio between the mole and Avogadro's number, which we know is 6.02 times 10 to the 23 polonium atoms, all right? So basically, when you do this calculation here, up to this point, you'll get the number of atoms in 1 mole. So the next step is to find the mass of the 1 cell, or the atom in the 1 cell. So that would mean that the molar mass would come into play here. And if you look up the molar mass of polonium, it's going to be 208.998 grams, according to the information I have in front of me. And you work this out. Now, this mole will cancel out with this mole. So your final answer here would be 3.47 times 10 to the minus 22 grams when I work it out. And therefore, to find the density, we take the mass here that we just calculated for the 1 atom in the cell and divide it by the volume of the cell by using this number. So of course, we know that the density is equal to mass over volume. The mass is 3.47 times 10 to the minus 22 grams divided by the volume of the cell, which would be given by, let me see here, which will be given by this number right here, 3.79 times 10 to the 7 picometers. But typically when it comes to solids, we express the densities in grams per cm cube. So we need to convert the picometers to centimeters cube. So that relationship would be 1 picometer, we do it down here, 1 picometer would be equal to 10 to the minus 2 centimeters. And all of this would be cubed, all right? And then we work it out. And when I did that this morning, the answer I got is 9.15 grams per cm cube. So that's basically how we answer the B part. Let me just check something here. B part, yes. So that's basically how we determine the density of polonium in this example based on the information given, all right? Any questions about this? Okay, moving along. Let's move on to the next example. Now, in the next example, it's talking about nickel, all right? It says the edge length of a unit cell for nickel is 0.3524 nanometers. They gave you the density, and the question is asking, does nickel crystallize in a simple cubic structure? And you're to explain. So this is kind of like the reverse of what we just did, all right? The only difference is that they gave us the density, right? In the first example, we are asked to determine the density. And based on that, we are to say whether or not nickel will crystallize in a cubic structure. In order for us to answer this question, I think we need to know the density of nickel. So let me look that up. Let me go here. Let me go here. Okay. Let me go here. Okay, I don't know what's going on here, so let me do this. Density of nickel. Okay, so according to this, the density of nickel is 8.9 grams per mil. So let me write that. Well, let me get rid of this first. So the density of nickel is equal to 8.9 grams per mil. So what we're going to do is see if, based on the information provided in the question, the density will actually be 8.9 grams per mil. So if the structure is simple cubic, then we know, based on what we did in the first example, that the number of atoms per unit cell is 1 atom, in this case, nickel atom, per cell, all right? If it is simple cubic, okay. So again, we go through the steps as we did before. We find a mole, so 1 mole of nickel, go up top, and the Avogadro's number go down here, times 10 to the 23 atoms, nickel atoms. And then the next step is where we look at the molar mass, which is, I looked it up earlier, 58.693 grams of nickel for every 1 mole of nickel. And when I did this calculation, the answer I got is 9.746 times 10 to the minus 23 grams. All right. Now the volume, as in the case of the simple cubic example that we did before, the volume would be equal to the length cubed, right? Now the length is equal to 0.3524 nanometers, 0.3524 nanometers, all right? So basically, in fact, let me just skip this and just go directly to the density calculation. The density will be equal to the mass, which is 9.746 times 10 to the minus 23 grams, divided by the volume, which is the length cube, which is 0.3524 nanometers. And again, as I said before, we typically convert this to centimeters cube or centimeters. So that would be 10 to the minus 7 centimeters equal to 1 nanometer. And we cube all of this right here. And when we do that calculation, according to my calculation, the answer for the density for nickel, based on the information provided, is 2.23 grams per cm cube. All right. And if you compare this density to this density, you see that they're not the same. So therefore, basically, the conclusion we can come to in answer to this question, does nickel crystallize in a simple cubic structure? The answer is no, all right? And that's because the density that is given for nickel is not the same as the density that is calculated based on the assumption that its arrangement or its crystallized structure would be a simple cubic. So therefore, this is not the density of nickel. Therefore, nickel does not have a simple cubic structure. All right. So that's basically how that example works out. Okay. Any questions about this particular example? Any questions? Okay. So the next example, let's see here. I think the next example has a different structure. It's talking about the face-centered cubic structure. All right. Okay. So, and this is talking in reference to calcium. So it has a face-centered cubic structure, and the edge length of its unit cell is 558.8 picometers. So the question is, what is the atomic radius of calcium in the structure? So again, we have to get a three-dimensional feel for the structure. Face-centered basically means that you have on one face of the crystal structure of the cube, you have a whole atom of the element here, while the corners basically will have 1/8 of an atom each, all right? So that's the face-centered cubic structure, right? Now, in this diagram here, they only showed you one face in terms of the atom occupying that face. But the other faces will also have an atom here, one below, one to the left, and one behind, which we can't see, all right? So this is just giving you an idea as to what we're working with when it comes to answering this question. The first of which is, what is the atomic radius? So if you look at this here, and of course, again, just as in the previous diagram, the nearest atoms are touching each other, right? So if you look at this atom here, it has, of course, you know, a radius, which is 2 times the diameter. And then for the atom that is here, from here to here would be the radius of that atom, and from here to here would be the radius of that atom. And they're all the same atom, which is calcium. So therefore, the total distance from here to here would be equal to 4 times the radius of one atom, all right? And you'll notice that we said before that each edge of the cell has a length, which is equal to 558.8 picometers, all right? So that's the A right here. So we have to do a bit of trigonometry to solve for R, all right? So let me remove this here. Okay, so to solve for R, we have to use Pythagoras' theorem. So if you go back to this diagram right here, right, you have a triangle right here, right, where 4R would be the length of the hypotenuse, all right, in this triangle. So the equation that you would write here would be Pythagoras' theorem as it applies to that particular arrangement, which would be A squared plus A squared is equal to 4R squared equal to 4R all squared, all right? So that would be the equation describing what's happening as far as that triangle is concerned. And we can simplify this to get 2A squared is equal to 16R squared, which means that that cancels with that to give you 8, which means that R squared would be equal to A squared over 8, which means that R will be equal to A divided by the square root of 8. So when you plug in the values for A would be equal to 55 or 558.8 picometers divided by the square root of 8. And let me do that calculation. I don't think I did that one this morning. So 558.8 divided by the square root of 8. And according to my calculation, this works out to be equal to, now I have to round off to 4 sig figs. So that works out to be equal to 1.976 times 10 to the minus 2 picometers. All right, so that would be the radius of, what's the element here? Of the calcium atom, all right? So that answers the first part of this question, this example. The second part is asking for us to calculate the density of calcium based on what we just did and based on the assumption that it's a face-centered cubic structure. So again, we have to get a feel for the three-dimensional arrangements that's taking place here. Now, if you remember, we said, right, in the previous example, that whenever an atom occupies a corner, it's basically 1/8 of an atom being contributed to that unit cell for each corner, right? Now, that is true in this case right here. In the case, however, of the atom occupying one face, if you think about it in 3 dimensions, basically there are 2 unit cells that will be sharing that atom. So basically 1/2 of an atom occupying the face right here would be contributed to this unit cell, and the other half will be contributed to the adjacent unit cell, right? And because there are 4 faces, that means that there, as far as the face-centered atoms are concerned, actually 8 faces, I'm sorry, 8 faces in the cube. So as far as the face-centered atoms are concerned, there are 8 of them. So therefore, the total number of atoms in this half cell, or this cell, I should say, would be equal to, so let me put here, number of atoms per cell in this case would be equal to, as we said before, 8 times 1/8 for the atoms in the corner. And in the case of the faces, it's 6. I think I said 8 faces. There are 6 faces. It's 6 times 1/2 in terms of the atoms that are being shared on the face, all right, of the cube. So when this adds up, you're going to get 1 plus 3 equals 4 atoms, right? So therefore, there are basically 4 atoms per cell in the face-centered cubic arrangement. So with that out of the way, we can start by writing down 4 atoms per cell. And we do the same thing with Avogadro's number that we did before to find the moles. So 1 mole over 6.02 times 10 to the 23 atoms. And then we do the molar mass, 1 mole of the atom divided by, or I should say on top, you should have 40.08 grams for the calcium. And when I worked this out, I got 2.663 times 10 to the minus 22 grams for each cell, all right? So that gives you the mass, but we're not finished yet because we need to find the density. So what I'm going to do is erase part of the work that we did before for A above and continue up there. Okay, so density, of course, will be equal to mass over volume. We just got the mass right here, which is 2.663 times 10 to the minus 22 grams divided by the volume. So the volume would be the length of one edge cubed. The length of one edge would be we have it here as 558.8 picometers. And again, I would convert this to centimeters. Let me see. 1 picometer will be equal to 10 to the minus 10 centimeters, okay? And then, let me see here. What did I write down here? And then we cube this, right? And work this out. And according to my calculation, this works out to be equal to 1.526 grams per cm cube. And that's how that is done, all right? And that's the B part completed. Okay, any questions about this one? Any questions about this example? Okay, so one last example in regards to unit cell calculations. So in this example, let me go to this here, scroll down. Again, face-centered structure for a different element, silver. It gives you the length of the edge. And the first question is, what is the atomic radius of this atom? So based on the formula that we used before, the radius would be equal to A, the length of the cube, divided by the square root of 8. So the length of the cube is given as 409 picometers, divided by the square root of 8. 409 divided by the square root of 8. And according to my calculations, this works out to be equal to, rounded out to 3 sig figs, 1.45 times 10 to the minus, times 10 to the 2 picometers, which is the same thing as 145 picometers, all right? So that would be the radius of the atom based on the face-centered cubic arrangement. So that's the A part. The B part is asking for, we'll go back to the original question, the density. Okay, so to get the density, again, it's the same thing as we did before. We know that density is equal to mass over volume. All right. The volume would be equal to the length cube. And the density, of course, we get it as we did before. So we start off, with 4 atoms per cell because it's face-centered cubic. And we multiply that by 1 mole divided by Avogadro's number, atoms. And then the next is where we use the molar mass, so 1 mole. And the molar mass of silver is 107.9 grams for 1 mole. And that gives us the mass, the total mass of the 4 atoms in the unit cell, which is 7.17 times 10 to the minus 22 grams. And then we do the density calculation. Density is equal to the mass, which is what we just calculated, minus 22 grams, divided by the volume, which is 409 picometers cubed, but we have to convert that to centimeters. So let me see here, what's the relationship? 1 centimeter is equal to 10 to the, because 10 to the minus 12, so that would be 10 to the minus 10. So this should be, I'm sorry. One picometer would be down here, and 10 to the minus 10 meters will be up here. And all of this will be cubed. And according to my calculation, this works out to be equal to 10.5 grams per CMQ. All right. Okay. So that's how that is done. Any questions about this one? Any questions? Okay. So that's basically all I have for you today. I may post a video later on with some other examples if I have the time to do so. But that's basically all I have for today. So let me just say that I will be posting a quiz assignment on Monday, which is based on the last 2 chapters. All right. So look out for that. And that will be due on the Friday of next week. And of course, there's a test that is still up there online. I hope you have been working on it. The deadline for that would be tomorrow. All right. So any other questions, generally speaking, before we leave?
No, sir.
All right. So that's it for today. I think I told you the last time that from now on, what's going to happen is that I'm going to make myself available on Skype during the regular class time, right? And I'm going to make also an announcement about when your final exam will be, maybe by the end of next week, all right? Or even earlier, you know. So basically, if you have any questions, in addition to contacting me during the office hours, you can also contact me during the regular class times, you know, Tuesdays and Thursdays, 9:30 to 10:45. All right. And I think that's it. I don't think there's anything else I have to say by way of announcement. So that's it. Enjoy the rest of your weekend, and we'll be in touch. All right.